Some structures and formula naming based on this simple cyclopentane. We have a cycle, and we have 5 carbons present. The carbons aren't drawn, nor are the hydrogens. It is up to you to imagine a carbon and 2 hydrogens off each one. This is a 3D, this is a model of cyclopentane. And I also didn't include the hydrogens because to keep it kind of simple here. Note that it's not flat. It's kind of puckered up on the one side here. It's not a flat 5 carbons. To try to make it flat, I can make it flat, but I can feel the tension in the bonds. It feels, there's much less strain going on there if it's kind of puckered up there in that thing right there. So cyclopentane at room temperature is going to go through a motion where that puckering kind of flips up and flips back down. Right here, we would just call this cyclopentane. Now, what if we put a methyl group like on that carbon right there, on the carbon coming off the top? If we put a methyl group on that carbon coming off the top, it looks something like this in its structure here. And we would call this methyl cyclopentane. The 2 best tips I can give you is that the number of carbons in the name has to equal your picture and to read it backwards. There is 1, 5, 6 carbons in this name. There are 6 carbons in these structures here. And if we read it backwards, the parent chain is cyclopentane and the methyl comes up. We could also call this 1-methyl cyclopentane. The 1 is kind of redundant. There's only 1 substituent on there. Now, if we move this methyl around, let's say we put this methyl here. We didn't do anything to the structure, okay? It's still the same compound. We've just turned it. Remember, these molecules are moving all the time, every time. So just because we move this substituent, it's still methyl cyclopentane. Now, if we have another substituent on there, let's say we have an ethyl. So we have 5, 6, 7, we have 8 carbons in this structure here. So we need to have 8 carbons in our name. We're going to read this backwards. So we still have cyclopentane because that's the parent chain. And we have to give locations to these substituents, either a numbering of 1, 2, or 3. The larger one gets the automatic designation of 1. And then we count around to the second one, 1, 2, 3. Now, in this particular case, it's important I count clockwise. If we were to count this direction, it would be a 1, 2, 3, 4 location. And why would that be incorrect? It's too complicated, too high of a number. We want our substituents to be the lowest numbers possible. So this is 1-ethyl, 3-methyl, see if I can fit this in here, cyclopentane. The number of carbons in our name is 2, 1, 5, 8, and there's also 8 in our picture here. And I can build a model of that as well. My cyclopentanes in the center. This is automatically 1 because it contains the ethyl. And if I go 1, 2, 3, 3 methyl. Let's do one more with this cyclopentane parent ring. I have my cyclopentane parent ring. It's the longest chain of carbon atoms. Each carbon is bonded 4 times. And we have a carbon here that's bonded 4 times that has 0 hydrogens on it. Let's write our name out. Cyclopentane. Now I have 2 substituents, but they're on the same carbon. This carbon automatically gets called 1, and we could call this here's our 3D structure of it, where we have our 5 carbon ring, and then there's the ethyl and the methyl. Note that there's a little bit of freedom here in how this ethyl can rotate. We would call this ethyl methyl cyclopentane. You could put the 1s in there. It wouldn't be wrong, but you may not see the 1s in there. 1 ethyl, 1 methyl cyclopentane. I hope this helps. Thank you.